Imagine you are right about to jump into this massive high-stakes meeting.
Oh, the worst possible timing.
Exactly. You're stressed, you click a vital link, or you ask your enterprise AI a quick, critical question, and bam, you're met with that dreaded four-error knowledge not found.
Or just that spinning wheel of doom.
Yes, the spinning wheel. It's just incredibly frustrating.
Right.
But the crazy thing is, every single time you ask an enterprise AI question, there is, well, a very high probability that the massive infrastructure supporting it is actively failing.
Right. Somewhere out there, a fiber optic cable is acting up, or, a server is overheating.
Exactly. An API region is having a micro outage, the system is breaking down, yet you hit enter, and like 1 second later, you get a flawless answer.
It's basically magic.
Feels like magic.
Right.
But today, we are looking at the actual architectural magic trick that makes that possible. We're talking about engineering systems that absorb chaos so that you, the end user, never even notice the 404 error happening behind the scenes.
And it fundamentally changes how you view cloud architecture. I mean, we're so conditioned to think about high availability in terms of building these indestructible walls.
Right, like a fortress.
Exactly. But the reality of modern large language model operations, or LLMOps, is that indestructibility is just a myth. It doesn't exist.
Right.
The real innovation is designing systems that know exactly how to stumble without actually hitting the ground.
Which brings us to our source material for this deep dive. We are unpacking this fascinating technical post by Aaron Rose, published on tech-reader.blog. It's called The Secret Life of Azure No More 404, Knowledge Not Found.
It's such a great read.
It really is. And our mission today isn't just about software engineering. It's about exploring the art of building systems that know how to fail gracefully. And Aaron Rose uses this brilliant framing device to explain it all.
Yeah, instead of a dry white paper about server racks and load balancers.
Yeah, exactly. Instead of that, the post visualizes this complex Azure infrastructure as a grand, old-world Victorian library in London. It's so vivid. We follow these two engineers. There's Margaret, who is this wise senior engineer, and Timothy, this sort of worried, anxious junior engineer.
What's fascinating here is how Aaron Rose uses this old world library setting to explain cutting-edge cloud infrastructure.
Yeah.
I mean, it makes the abstract concept of high availability incredibly tangible.
It really does.
The library is just a perfect physical metaphor for an LLM application. You have massive archives of data, these complex retrieval systems, and, well, a user standing at the front desk who just wants a quick, accurate answer.
Right. They don't care how the books are sorted.
Exactly. They just want their book. And Timothy, the junior engineer, he's looking at their primary AI model, which they call the lead planner. And he realizes they have this terrifying vulnerability.
And it's a vulnerability that, honestly, anyone building on top of OpenAI or Azure APIs right now has to confront. Timothy points out that they do have safety nets in place, right? Like, they're using guardrails to catch lies or prevent the model from hallucinating.
And they have canaries, too.
Right, canaries, which basically means they're routing a tiny fraction of live traffic to test models to catch, what's it called, logic drift, where the AI slowly degrades in its reasoning over time.
Right. It gets a little dumber.
Yeah, exactly. But despite all that sophisticated monitoring, Timothy realizes the lead planner itself is a single point of failure. If the Azure region hosting that primary model goes down, the whole library just vanishes. Poof.
Yeah, Margaret calls this the fragility trap. It is an all-or-nothing system.
The fragility trap.
If a system cannot operate at 100% capacity, it just instantly defaults to 0%. And for a high-stakes enterprise environment, I mean, an all-or-nothing architecture is basically a ticking time bomb.
Okay, let's unpack this for a second, because my initial reaction to reading about this fragility trap was, well, a bit of skepticism.
Really? How come?
Well, with the billions of dollars poured into redundancies by major cloud providers, isn't the goal of modern tech to just build a system that never goes down? Like, why are we accepting failure as a starting point?
I get that.
It just feels like giving up before you even write the first line of code,
Well, the problem with demanding perfect reliability is that you're essentially fighting physics and statistics.
Okay, fair.
You cannot control a backhoe severing a fiber line in Nevada.
Right.
And you cannot control sudden, massive spikes in global API demand. If your foundational architecture assumes perfect conditions, it's just going to shatter the moment reality sets in.
So perfection is the enemy here.
Exactly. Real resilience requires moving from this idea of a total outage to what the article calls graceful degradation. You acknowledge that components will break, and you control the descent.
You control the descent. I like that. And Margaret visualizes this controlled descent in the story by taking out this cobalt blue marker and drawing what she calls a degradation ladder.
The ladder is such a great concept.
It really is. Instead of a single primary AI, they use a multi-model redundancy strategy. So run 1, the very top of this ladder, is the light planner. This is your heavy, highly capable model. It handles the most complex stuff.
But when that top rung breaks, you don't just kick the user out of the library.
Right, you don't lock the doors.
Exactly. The system instantly steps down to rung 2, which the text refers to as the scout.
The scout.
Yeah. And in this specific setup, they use GPT-4 Mini as the scout. It's fundamentally different from a massive flagship model. It has fewer parameters, which means, it might miss the subtle nuances of a really complex prompt.
It's a little less nuanced, yeah.
But it's fast.
Yeah.
And it's alive. Its inference speed is incredible. When the primary system is under duress, you gladly trade a slight drop in deep reasoning just to keep the lights on.
But the ladder doesn't stop there, right? Because what if rung 2 breaks? If the external API hosting the Scout also goes dark, the system steps down to rung 3, which is the tiny model.
Right. They mentioned Phi-3 for this role.
Yes, Phi-3.
Yeah.
And what really stands out to me here is that this model isn't even relying on the cloud. It's run locally.
On their own hardware.
Exactly. The answers get a lot simpler, maybe just basic summarization, but the library never locks its doors. I was actually thinking about this whole ladder concept in the context of like a Michelin star restaurant.
Oh, I love a good food analogy.
Right. So if you have this visionary head chef, that's our lead planner, and they suddenly faint in the middle of a busy dinner service, an all-or-nothing system would basically pull the fire alarm and throw all the diners out into the street.
Just total chaos.
Total chaos. That's a 404 error. But a system with graceful degradation, it has a sous chef ready to step in. That's the Scout. The plating might not be a work of art, but the food comes out fast. And if the sous chef goes down, well, fry cook takes over. That's the tiny model. You're only getting a burger and fries at that point. But hey, you're still sitting at a table eating a meal.
Exactly. You're still being served. It isolates the core utility from the premium experience.
Right. Now, having a ladder is great. But it poses a pretty logical question. How does the system actually know when to climb down without leaving the user waiting forever?
Yeah, the timing is tricky.
Like if I submit a complex query and the lead planner is just struggling to process it, how does the system know the difference between a model that is just thinking really hard and a model that is functionally dead?
You definitely can't leave the user staring at a loading screen for 30 seconds.
Exactly. Margaret solves this with a brilliant stopwatch analogy. Instead of waiting for a total crash or an official error code, the system measures something called P99 latency.
Yeah, for anyone who manages like a Grafana dashboard, P99 latency is a standard health metric.
Right. It means looking at the 99th percentile of your response time.
Exactly. It shows you the worst case scenario your users are experiencing. But they aren't just looking at it on a dashboard here. They're using it as a hard trigger.
A hard trigger.
Yeah.
So how did that look in practice?
Well, let's say the lead planner normally takes about 800 milliseconds to start responding. Margaret configures the system with a hard threshold, say, 2 seconds.
Okay, 2 seconds.
If that P99 latency breaches 2 seconds, the system doesn't wait around for Azure to say, hey, we're broken. It just assumes a hiccup is happening and immediately drops to the Scout.
So the user experiences, what, maybe a 2.5 second delay?
Yeah, which just feels like a tiny bit of lag.
Right, a minor lag. But behind the scenes, a complete architectural failure was seamlessly bypassed. That is so cool.
It really is.
But Timothy brings up his next very valid concern. Because if the latency triggers the fallback, and all new traffic is suddenly hitting the Scout, won't the system just keep hopelessly knocking on the door of the dead lead planner API?
Yeah, if a server is already broken, bombarding it with a continuous stream of requests is just going to cause a cascading failure.
Right. Here's where it gets really interesting. To prevent that cascading failure, Margaret introduces the circuit breaker.
Such a crucial component.
She visualizes it as this heavy, industrial cobalt blue switch. And the mechanics are beautifully simple. If the primary model fails or times out 3 consecutive times, the switch physically trips into the open position.
Just like the electrical panel in your house.
Exactly like that. And once it trips open, the gateway severs the connection entirely. For 5 whole minutes, absolutely zero traffic is allowed to even try reaching the lead planner. Everything routes straight to the fallback.
It gives the primary system time to breathe.
Right. But a trip breaker creates a new problem, doesn't it? Because you don't want to run your enterprise application on a lower-tier fallback model forever.
No, of course not.
You need the primary model back online the second it recovers. But if you just wait 5 minutes and slam the breaker shut, you're flooding all the traffic back at once.
Which would just immediately crash it again if the outage isn't actually fixed.
Right. So how do they handle that?
This is where we get to the half-open state. It's a really brilliant nuance from the text. When that 5-minute timer is up, the system doesn't fully close the circuit. It enters this cautious, probationary phase.
Cautious is the key word.
Yeah. It opens the connection just a crack and allows exactly one test request to pass through to the lead planner.
Just one.
Just one. If it works, the system registers that things are stable, the breaker fully closes, and normal routing resumes.
But if it fails...
Breaker snaps open again, the timer restarts. If we connect this to the bigger picture, Margaret has this profound summary of this state. She says, "We stop knocking on a door that won't open, but we keep checking the lock."
We stop knocking on a door that won't open, but we keep checking the lock.
That is so good. It perfectly balances self-preservation with readiness.
Okay, so we have the degradation ladder, the P99 latency trigger, and the circuit breaker.
Yeah.
But what if the absolute worst-case scenario happens?
The apocalyptic scenario.
Right. What if the basement floods? What if the Azure region goes down, the Scout is unreachable, and the local hardware running the tiny model catches fire?
You're out of rungs on the ladder.
Exactly. Margaret visualizes this final stage by drawing a solid concrete floor beneath the ladder, the ultimate fallback.
And it isn't even an AI model at all.
No, it's not. It's just a static message. It basically says, the library is experiencing high volume. Please rephrase or try again in a moment.
It's an admission of defeat, but, it's an honest one.
Wait, let me push back on that a bit,
Yeah.
because there's a huge debate in product design around that kind of honesty.
Oh, for sure.
Doesn't admitting your system is struggling make users lose faith in the product? Like, if I ask a premium AI a question and it gives me a noticeably shorter answer or tells me it's overloaded, my first thought is that the platform is just broken.
Well, this raises an important question, and the source material tackles that exact anxiety with this concept of degradation transparency.
Degradation transparency.
Yes. And it makes a really compelling counter-argument. It argues that hiding the degradation actually damages trust far more than admitting it.
How so? Walk me through that.
So Margaret institutes a rule for the UI. Whenever the system relies on the Scout, the tiny model, or a cache, the front end appends a tiny little lightning bolt emoji, just a little no, next to the response.
So you're explicitly telling the user, hey, you're eating the sous chef's food right now.
Exactly. Because if you hide it, the user reads the response, sees it lacks depth, and just assumes your AI is getting dumber.
Right, they think the quality is dropping.
But if you show them that lightning bolt, it tells them the system is running at reduced capacity. It tells them you prioritize their access over the illusion of perfection. Transparency actually builds trust when the lights are dim.
That makes total sense. Managing expectations in real time. And all of this builds up to the climax of the story, which I absolutely love.
Oh, the outage.
Yes. Late that night, a real regional API outage actually hits. Timothy is watching the dashboards. The latency on the lead planner spikes past 2 seconds. The system instantly intercepts the traffic and routes it to the Scout.
The circuit breaker registers the failures, trips open, severs the connection.
The half-open state quietly tests the lock in the background every 5 minutes. And the users, they don't see a massive outage.
No, they don't.
They just see a little lightning bolt emoji,
Yeah.
and they actually feel like the library is a fraction faster. No one sees a 404 error. Timothy has this amazing realization as he's watching the dashboards. He says, we fell, but we didn't hit the ground.
Such a powerful line. It's the perfect summary of what cloud engineers are actually trying to achieve. You know the fall is inevitable, so you just focus all your effort on deploying the parachute.
Margaret caps her cobalt blue marker and delivers the whole takeaway of the story. The best systems aren't the ones that never break. They're the ones that know how to fail with dignity.
Failing with dignity. I love that.
So what does this all mean for you? Whether you're coding an app, managing a team, or just organizing your own life, you need to expect failure. You need a degradation ladder. You need a circuit breaker to stop you from banging your head against a wall. And you need a concrete, ultimate fallback.
And, this framework extends so far beyond software. Think about that half-open circuit breaker for a second.
Okay.
If software engineers are deliberately designing digital systems to fail with dignity and to gracefully step down to simpler tasks when they're overwhelmed, how might we apply that exact same graceful degradation to our own human burnout?
Oh, wow. That is a deep thought.
Right. What does your personal half-open circuit breaker look like when you're completely overwhelmed? Are you allowing yourself to drop to a tiny model when you need to, or are you just stuck in an all-or-nothing trap?
That is a phenomenal question to sit with. I think we all need to map out our own degradation ladders. Well, we are going to leave you to mull over your own personal architecture. Thank you so much for joining us on this deep dive into the secret life of Azure and the complex art of feeling gracefully. Until next time, keep checking the locks on those closed doors.